Hello everybody, my name is Ella Barati, the second year PhD student in computer science from Wayne State University. Today I am going to talk about loss and gain approach from the paper Scheduling Workflows with Budget Constraint. This paper was presented in Integrated Research in Grid Computing in 2007 from University of Manchester and University of Cyprus. I will start my presentation with the introduction. After that, I will talk about some background information and the proposed algorithm will be provided then. I will talk about the experimental result and finally, I finish my presentation with the conclusions. In the context of grid computing, a wide range of applications can be represented as workflows which are modeled as directed acyclic graphs. These directed acyclic graphs, each node represents tasks and the edge between nodes shows precedence constraint between two tasks. A DAG represents a model that helps build a schedule of tasks onto resources in a way that the precedence constraints are respected and the schedule is optimized. All existing works in the literature aims to minimize the total execution time of the tasks. Although minimization of an application execution time might be an important user requirement, managing a grid environment is a more complex task. In this paper, workflows applications are modeled as DAG, and the objective is to find the schedule that gives the shortest makespan for a given DAG and a given set of resources without exceeding the budget available. In order to solve the problem of scheduling optimally under a budget constraint, this paper presented two different approaches. One of them is called loss and the other one is called gain, which are both from the families of heuristics. In the loss approach, it starts with an assignment of tasks onto machines that is optimized for makespan. After that, it keeps swapping tasks between machines by choosing first those tasks where the largest saving in terms of money will result in the smallest loss in terms of schedule length. In the gain approach, it starts with the cheapest assignment of tasks onto resources. Again, it will swap the tasks between the machine by choosing those tasks where the largest benefit in terms of minimizing the makespan will be obtained for the smallest expense. In this paper, they are using the DAG model, and the DAG model follows some assumptions. First of all, each DAG starts with a single entry node and has a single exit node, and each node connects to other nodes via the edges which represent the node dependencies, and each edge has a value which indicates the amount of data that need to be communicated from the parent to the child node. For each node, we have two options. We have the execution time on each different machine and the time of communicate data between machines. And as we can see, here we have an example of a DAG with the computation cost of nodes on different machines. We have three different machines and also the communication cost between these three different machines. And here the schedule length which is produced by HEFT algorithm is shown here. And as we can see, there is no task even assigned to machine 2 because the communication is too high. HEFT algorithm assigns the tasks to machines which provide earlier finish time, and here no tasks satisfy this condition. In this part, we can see that we have different nodes and the start time and finish time of each node is shown here. Okay, the contribution of this paper goes through the extension of the traditional DAG models, because we know that each machine that is available has some cost. In fact, the usage of each machine available costs some money. As a result, an additional constraint need to be satisfied, and the overall financial cost of the schedule does not exceed a certain budget. Therefore, they define the overall cost as the sum of costs of executing each task in the DAG onto a machine. Therefore, we have CIJ, which is the multiplication of machine cost by the execution time. Execution time means the execution time of the task I on the machine J, and the machine cost means the cost of running something on assumptions. They proposed an algorithm. The key idea behind it is to satisfy the budget constraint by finding the best affordable assignment possible. In this algorithm, there are two definitions: best assignment and affordable assignment. What is the best assignment? The best assignment is the assignment whose execution time is the minimum possible, and the affordable assignment is the assignment whose cost does not exceed the budget available. Also, this algorithm contains some assumptions. The available budget should be higher than the cost of the cheapest assignment. This assumption guarantees that there is at least one solution within the budget available, and also the available budget is less than the cost of the schedule. Cost of the schedule is obtained by using a DAG scheduling algorithm, and without these assumptions there would be no need for further investigations. Okay, here we have the algorithm. The algorithm starts with an initial assignment of the tasks onto machines and then compute the weight values for each reassignment of each task to a different machine. Therefore, we have a weight table which is created for each task in a DAG for each machine. We have two approaches for computing the weight. One of them is called loss and the other one is called gain. And depending on the choice for the initial assignment, we will use one of them. If we use loss, the initial assignment is produced by an efficient DAG scheduling algorithm, like the heuristic algorithm. Otherwise, if we are using gain, the initial assignment is provided by allocating tasks to machines where the cost will be the least. I mean, we use the least money, so this assignment is called the cheapest assignment. In this algorithm, we have a DAG which is a workflow with task execution time and communication. We also have a set of machines with the cost of executing jobs, and also a DAG scheduling algorithm H. And our budget is available as the B. So we have two options, loss and gain. And if we use loss, we will generate the scheduling S by using the algorithm that we have. If otherwise, we will generate a scheduling by mapping each task to the cheapest machine. So based on this, we are going to make the table or the weight table for each task in each and for each machine. We will assign the task to the machine, and we check if the task is assigned to the machine. Therefore, the value for that task on the for that task and that machine on the table will be 0. Otherwise, we should compute the weight. But for the weights, we have two options: gain weights and loss weight. In the loss weight, for task I on the machine M, we have T old, T new. T old is the time of executing task I on the machine, which assigned by one of the algorithm like HEFT or something else. And T new is the time of execution time, task I on the machine M. We also have C old and C new. C old is the cost of executing task I on the machine given by one of the algorithm, and C new is the cost of executing task I on machine M. So if C old is less than or equal to the C new, the value of loss weight will be 0. For the gain value, weight, we also have the same things. By using the weight tables, we can select the tasks to be reassigned to the machines, and we will continue these things until the cost of the current schedule is more than the budget, or until there is no money available. So if our approach is loss, we have one condition: the cost of the schedule should be more than budget. But if we are not using loss, the cost of the schedule should be less or equal to the budget. So until the condition is valid and there is all reassignments have not been done yet, so we will check if we have the approach loss. So we find the smallest non-zero value from A. Why? Because in fact the tasks are used to be reassigned by considering the smallest value of the loss weight. If we use gain, so we find the biggest non-zero value from A, and we will reassign the task I to machine J in the schedule, and we will continue the cost, calculate the cost of the schedule. If we have gain and the cost of the schedule is more than the budget, then the previous reassignment is invalid. After that, we will check if the cost of the schedule is more than the budget, then we will use the cheapest reassignment for S, and at the end we will return the schedule. And for each of two approaches that we talked about, loss and gain, we consider three different variants and which are used for computing the weight. In the first variant, loss 1 and gain 1, the weight are computed exactly as described before, like the loss weight and gain weight. But for the loss 2 and gain 2, the values for T new, T old, T new, C old refer to the benefits that overall cost and make span have for the schedule, not the benefits of just one task that is considered for the reassignment. And the other one is loss 3 and gain 3. In this part, the weights are recomputed each time a reassignment is made by the algorithm. In order to evaluate each version of both approach, this algorithm was run with 4 different types of DAGs: FFT, fork join, Laplace, and random DAGs. And all DAGs contain about 100 nodes, and they scheduled on 3 different machines. They run the algorithm 100 times for each type of DAGs and consider the average value as the result. In this algorithm, they also have the possible budget, and the possible budget computed by the cost of the cheapest assignment plus the subtraction of the total cost of the assignment, which produced by the DAG scheduling heuristic like HEFT, which used for the initial assignment when we are using the approach loss, and the total cost of assignment minus the cheapest cost by one coefficients or one weight, which is between 0.1 and 0.9. So in order to compare the quality of the schedule produced by the algorithm for each of 6 variants and each type of the DAG, since there are 100 experiments, the normalized schedule length will be computed through this equation, where t value is the make span returned by the algorithm, t DAG is the make span of HEFT or other type of heuristic algorithm, and t cheapest is the make span of the cheapest assignment. The cheapest assignment is expected to be the worst, and t DAG is expected to be the shortest. Therefore, we expect to have the result between 0 to 1, which indicates how close the algorithm was to each of two bounds. But in each case we take 100 run, and the average value can help us. Therefore, the average normalized difference metric can be computed through the this equation, where the subscript I denotes the iths run. And here we have the result on end of each type of DAG with loss approach when HEFT is used as an initial assignment. And in this page we have average normalized difference for 3 different variants of gain, and as we can see, loss have better make span than gain, and they are much closer to the baseline because loss starts with a DAG scheduling heuristic, which already produce a short make span, but gain starts from the cheapest assignment whose make span is long. However, as we can see, the budget is close to the cheapest budget. And here the running time for the algorithm is provided to evaluate the performance of each version of the algorithm by using both loss and gain approach. They extracted from the experiment, and they just provided the result of FFT graph as it's illustrated here, and they used HEFT and HBMCT algorithm for the initial reassignment. And as we can see, gain approach takes longer than loss. Also, the third variant of loss takes longer than the others because it involves recomputations of weights after each reassignment of tasks. And for the conclusion, an algorithm was implemented to schedule DAGs on 2 heterogeneous machines under budget constraint. Also, different variants of the algorithm were modeled and evaluated, and starting from the optimized schedule in terms of its make span, payoff when trying to satisfy the budget constraint. And in the future work, they're gonna check the other type of the DAGs that correspond to the workflows, and they also more sophisticated models will be incorporated, and more dynamic scenarios and environment for executions of the DAG and modeling of the machine will be considered. Thank you for listening to this presentation.